Hello everyone, welcome to this lecture series in Differential Calculus. This is lecture 5 and today we are going to talk about derivative of a function of a single variable. At first we will define the derivative at a point. So the derivative of a function f at a point x naught denoted as f dash x naught and is given by this limit of difference quotient provided that this limit exists. Okay, so let x naught be any point in the domain of function, and so let p be the corresponding point on the curve, and let x naught p plus h be the neighborhood point and the corresponding point on the curve be q. Then this change in x will be h and the corresponding change in y will be the function value at q minus the function value at p. Okay, and as we have discussed this in the earlier lectures also, so this difference quotient is nothing but the slope of the secant, and when h goes to 0, that means if this neighborhood point goes to x naught, then the corresponding point q on the curve will move towards p point. Okay, so the this secant will become a tangent to the curve at the point p. Okay, so this limit h goes to 0 of the difference quotient can be interpreted as the slope of the curve at the point p. Okay, so the following interpretations for the limit of the difference quotient for this right hand side, if limit exists, that we can say that it represent the slope of the graph at the point x naught. Okay, also because this secant becomes the tangent, so we can also say that it is the slope of the tangent at point p. Okay, and if we interpret this difference quotient as an average rate of change, then that means the derivative gives the function's instantaneous rate of change with respect to at x naught. So we can also say that this gives us the rate of change with respect to x at x is equal to x naught, that means at the point p. Okay, so it can be uh, interpreted as the instantaneous rate of change at point p. Okay, and of course we are calling that this is the derivative of a function at the point p or at the point x naught. Okay, uh, so these are all interpretations for the derivative at a point. Here I have used the notation of prime. Okay, so f dash x naught means the derivative of function at the point x naught, and this notation was used by Newton. There is another notation that we can also write derivative as df by dx if we are differentiating with respect to x. Okay, and so we can write df by dx at the point x naught, and we will d by dx is like an operator notation similar to what Leibniz used. Okay, so now we can define the or generalize this to derivative as a function. Okay, so we can now define the derivative for by considering the limit at each point x in the domain of function instead at a particular point x naught. Okay, so the derivative of the function fx with respect to the variable x is the function f dash whose value at x is, where x is any point of the domain, is f dash x, which is equal to limit h tends to 0 f of x plus h minus fx over h provided the limit exists. Okay, so it's just the generalization in the sense that instead of one point of x naught, we are saying that we can calculate derivative at each point x where the points x are in the domain of the function. There is an alternate formula for writing this right hand side. If I call this neighborhood point x plus h as z, then I can rewrite this right hand side as f of z minus fx, and so if I am writing x plus h as z, then h can be written as z minus x. Okay, so this h here will be z minus x, so it is same as z approaching x. So z is the neighborhood point of x, so z approaching x of fz minus fx over z minus x. Okay, so both these definitions are same. Okay, and the important points are that the domain of the f dash, the derivative, is the set of points in the domain of f for which the limit exists. Okay, so that will mean that the domain may be the same as the domain of f, or it may be smaller than the domain of f depending upon the right hand side limit. Okay, and if derivative exists at a particular point x, we say that function is differentiable or has derivative at x. And if f dash exists at every point in the domain of f, then we call f as differentiable function. Okay, the process of calculating a derivative is known as differentiation. Okay, and we have two type of notations here, the prime notation or operator notation. That means I can represent the derivative as f dash x, or if y is equal to fx, then I can represent it as y dash or f dash, or I can also write dy by dx as derivative of a function. So now let us take say one example that differentiate this function fx is equal to x over x minus 1. Okay, so by definition, if fx is equal to x over x minus 1, then at any neighborhood point f of x plus h, we can write it as x plus h over x plus h minus 1. And so the uh, derivative of the function at the point x by the definition will be limit h tends to 0, the difference of the y values to the difference of the x values. Okay, so f of x plus h minus fx over h. Okay, so we can substitute these two in the numerator, and then we can solve this, okay, by taking LCM. Okay, so those are easy steps, and then we can cancel out some terms, because limit h goes to 0 on this, so h is a non-zero number here, so we can cancel out h in the numerator and denominator to write this as limit h tends to 0 of minus 1 over x minus 1 plus x into x plus h minus 1. So as h goes to 0, then this limit value is minus 1 over x minus 1 square. So this is the derivative of the function fx at each point x in the domain of function. Okay, uh, so now we further define what are differentiable functions on an interval, and the one-sided derivatives. A function y is equal to fx is differentiable on an open interval, whether that interval is finite or infinite, if it has derivative at each point of the interval. Okay, so as I said earlier, that we call a function differentiable if it is differentiable, or if it has derivative at every point of the domain. Okay, so if you are given domain as an open interval, then we will call it differentiable if it has derivative at each point of this open interval. Okay, and if the interval is closed interval, okay, so we call this function differentiable on a closed interval if it is differentiable on the interior. Okay, so that means in the open interval AB, and if the uh, limits, that means if the derivative at the end point, and at the end points, because uh, the only we can calculate the derivative from the left or from the right, then the one-sided derivatives at the end point, if those exist, then we say that it is differentiable in closed interval. So if the limits uh, at the lower end point, we will have a right hand derivative. Okay, Okay, so because A is a lower end point, so we can only approach from the right to this point A. Okay, so the right hand derivative at A and the left hand derivative at B, okay, at the upper end point. Okay, if the left hand derivative at B, okay, if both these exist at endpoints and if the function is differentiable in the interior, then we say that it is differentiable in the closed interval AB. Okay. So when we can say whether the function is uh, not having a derivative at a point. Okay. So function we said that has a derivative at a point x naught if the slope of the secant line through the point P and the neighborhood point Q on the graph approach a finite limit as Q approaches P. Okay. So whenever this fails, that means whenever if we take the secant line from P to the neighborhood point Q, and whenever this secant line fail to take the limiting position, or if it becomes vertical as a q point approaches p point, then we say that the derivative does not exist. Okay, so for like a function can fail to have a derivative at a point when there is a corner point. Okay, so like in this case, if this is your blue line is your function curve, okay, and we want to check the derivative at this point p, then you can take the say q to be the neighborhood point on the left one time to check the left hand derivative, and take the neighborhood point q on the right to check the right hand derivative. Okay, so if I take the neighborhood point q on the left first and then move this q point towards p, then you can see that this secant line, it moves and ultimately it becomes this tangent. Okay, similarly on from the right, if I take the neighborhood point q, then this is the secant line here, and as this q moves towards p, this secant line becomes this tangent. Okay, so because the left hand derivative this and the right hand derivative are not same. Okay, that means the one-sided derivatives give different values, then we call this as a corner point, and in this case derivative at this point do not exist. Okay, the second possibility is a cusp. Okay, okay, so we call a point a cusp where the slope of this secant approaches plus infinity from one side and minus infinity from the other side. Okay, so we can see that if I take this representing q minus point. Okay, so this secant, as this point q minus moves towards the point P. Okay, so what happens to this secant line? This secant line moves in this direction. Okay, so this is a positive slope. Okay, so this positive slope becomes vertical, so that means this slope becomes plus infinity. Okay, on the other side, if I take this q plus point and if I move this q plus point towards this p point, then this secant has a negative slope. Okay, so as it moves toward this side, this negative slope is becoming vertical, so this tangent from the right side is actually giving a slope of minus infinity. Okay, so the slope from this side is plus infinity. Okay, the positive slope becoming vertical. Okay, and the slope from this side is becoming minus infinity. Okay, so negative slope is becoming vertical, so minus infinity. So if slope from one side becomes plus infinity, from other side becomes minus infinity, then we call that point as a cusp. Okay, and the derivative do not exist at that point. Okay. The third possibility is that we say a vertical tangent where the slope uh, approaches either plus infinity from both sides, or it approaches minus infinity from both sides. Okay, in this particular example it is minus infinity from both sides. Okay, so you can say that if I take the point q negative on the left hand side and check the left hand derivative, then this is my secant, and as q negative approaches p, moves on here, then this secant moves here, okay, and it becomes vertical. So what is happening is the slope of this secant is negative, okay. So this negative slope, as q negative moves toward p, it becomes vertical, so negative slope becomes minus of infinity, okay. And similarly, if I take this point q plus on the for the right side derivative, then again the secant line, this p q plus, okay, the slope of this is again negative, okay. So this as q plus moves towards p, okay, this secant line becomes a vertical line, okay. So the slope which is negative becomes minus of infinity from right side also, okay. So from both side it becomes minus infinity, so we call it a vertical tangent. Also, if from both side we only get plus infinity, then also we say that it is a vertical tangent, okay. So again the derivative at uh, point p do not exist, okay. Okay, there are other cases also. For example, if you have a discontinuity like a jump discontinuity, or there is a removable discontinuity, okay, so you can again see that uh, in case of jump discontinuity, one of the derivatives becomes vertical, okay. So if I take q negative to be the neighborhood point to the left, then this is the secant, and as q negative moves towards or moves on the curve toward the p, okay. So this positive slope actually becomes vertical, so it gives a plus infinity value. On the other side, when this moves, then we get this tangent, okay. So on one side derivative is giving a plus infinity value in this case, okay. Also, if you have a say removable discontinuity, and the value at this point is here, so this is my p point, okay. And if I take the neighborhood point on the left side as q negative, so we have a uh, positive slope here as q negative moves on this curve towards this side where we have to check the limit, and so this positive slope becomes vertical, okay. So we get a plus infinity value. And also, if we take the point to other side and move it here, then this negative slope gives a minus infinity value, or again it becomes a vertical, okay. So if we get a vertical tangent, okay, then the derivative will not exist, okay. So in all these cases where you have jump discontinuity, or we have removable discontinuity, okay, so the derivative do not exist, okay. So that means if function is not continuous at a point, then the derivative at that point do not exist, okay. But if the derivative at a point exists, then at that point function must be continuous, okay. So we'll prove this important result of differentiable functions are continuous, okay. So differentiability implies continuity for a function of one variable, okay. So we'll prove this important result now, that if f has a derivative at a point c, then function is continuous at a point c, okay. So that means if you are given a function and c is x is equal to c is a point in the domain, and if the derivative of function at c exists, then function must be continuous at x is equal to c, okay. So to prove this, uh, given that the derivative at c exists, we must show the continuity condition that limit x tends to c on fx must be equal to f of c, okay. So the left and right hand limit and must be equal, and it must be equal to the function value at c, or uh, equivalently we can say that limit h tends to 0, f of c plus h must be equal to f of c. So if h is non-zero, then we define this f of c plus h equal to f of c. If we write that, if we add and subtract f of c to this, so we can write this f of c plus h as this f of c plus f of c plus h minus f of c, okay. And uh, if I take a limit h tends to 0 on this by rewriting the last two terms by multiplying and dividing with h, because h is a non-zero number. So and then if I take limit h tends to 0 on this, then the left hand side is limit h tends to 0 on f of c plus h, and right hand side is limit on this sum. And we know that a limit on sum is equal to sum of limits, so we can write limit on fc plus limit on this product, okay. So because limit on fx into gx we can write as limit fx into limit gx, and because this limit on fx is nothing but the derivative, okay. By definition, this limit h tends to 0 f of c plus h minus f of c over h, it is the definition of derivative at the point c. So we can write this as f dash c, and limit h tends to 0 on h will be 0, so it is f dash c into 0. So immediately we get that it is equal to f of c, okay. So it proves our continuity condition, and so we can see that whenever function has a derivative at a point, it must be continuous at a point, okay. So this is a very important theorem, okay. Now I define some differentiation rules uh, so that which allows us to differentiate functions directly without having to take the limits each time, okay. So we once we know that these rules hold, then there is no need to take a limit of the difference quotient and solve that, okay. So we can solve directly, and the first is that the derivative of a constant function, okay. So if f has a constant value, f of x is equal to c, okay, at all points x in the domain, then the derivative of function with respect to x is 0, okay. So this is the notation which is a operator notation similar to the prime notation, okay. So f prime is also derivative, and df by dx also denotes the derivative of the function with respect to x, okay. So I'll just prove this result by definition that the derivative of the function is limit h tends to 0 function x plus h minus function value x over h, okay. And because f of x is c for all x, so it is constant for the point x, and it is also constant in the neighborhood point, okay. So f of x plus h is c and fx is c, so the difference is 0, and so we get that the derivative of the function is 0, okay. So this is one result, that if the function is constant function, then the derivative is 0. Second result is derivative of constant multiple rule, okay. So if u is a differentiable function of x and c is a constant, then the derivative of c times u with respect to x is c times derivative of u with respect to x, okay. So again I'm proving this by definition, that derivative of cu, okay, and u is a differentiable function of x, so by definition we can write that it is limit h tends to 0, this function value at x plus h minus the function value at x divided by h, and because c is a constant, so we can take it outside, and so it is c limit h tends to 0 on this, and because u is differentiable, so this limit definition says that it is du by dx, okay. So derivative of constant times u is constant times derivative of u, okay, with respect to the same variable x. And similarly the power rule, if n is any real number, then the derivative of x power n is n times x power n minus 1 for all x where the powers x power n and x power n minus 1 are defined, okay. So this is the power rule, okay. So I'm not going to prove rest of the rule, and just show what rules are there, okay. So you can use these rules directly, okay. So you can calculate the derivative of x power n for any real number n as n times x power n minus 1. The derivative sum rule: if u and v are differentiable functions of x, then their sum u plus v at every point where u and v are both differentiable. Okay, so and at such points, okay, so if u and v are differentiable, then their sum u plus v is also differentiable. Okay, at all the points where u and v are differentiable. Okay, both are differentiable. So at such point, the derivative of u plus v can be written as derivative of u plus derivative of v. Okay, so derivative of sum can be calculated as sum of derivatives. Okay, the derivative product rule: if u and v are differentiable functions of x, then so is their product uv, and we write that derivative of product of function uv is u function into derivative of v with respect to x plus v function derivative of u with respect to x. Okay, so this is the derivative product rule. The derivative quotient rule: if u and v are differentiable at x, and if vx is non-zero for all x, then the quotient u by v is differentiable at x, and we write that d by dx of u by v is v derivative u minus u derivative v over v square. The chain rule: if y is a function of u, is differentiable at point u is equal to gx, and gx is differentiable at x, then dy by dx by chain rule we can write it as dy by du into du by dx. Okay, so if y is a function of u and u is a function of x, okay, then we can calculate the derivative of y with respect to x as derivative of y with respect to u into derivative of u with respect to x. So these are some of the rules which we can use without uh, calculating the limits each time, and we can calculate derivatives of functions. Okay. Now we'll talk about linearization. By linearization, we mean that approximating the functions based on the tangent lines. Okay. So what exactly we mean? Let us look at this example that say y is equal to x square be the function curve, and at a point we draw a tangent line to this. Okay. So by linearization means we can approximate the value of the function curve uh, by the value of the tangent line in the neighborhood or in the very close proximity of the point where tangent is drawn. Okay, so uh, see that we have to be careful about using this, because in the sense that the linear approximation can only be used in the neighborhood, and if we move away from the point where linearization is done, then normally the accuracy is lost. As you can see that as we move away, then the function and the tangent values at any point, say here if I check, then this tangent value is here but the function value is up here. Okay, so but in the very close proximity of this point where tangent is drawn, the function values can be approximated by the values on the tangent line. Okay, so this process is called linearization, and just to see that what happens near to this, if we zoom to this image in the neighborhood of 0.11, then you can see that tangents and curves are very close near to 1 point. Okay, and if we further zoom it, uh, then you can see that tangent and curve are very close throughout entire x interval used here. Okay, and if we further zoom into this, then you can see that they are, it is very difficult to distinguish that which is the y is equal to x square curve and which one is the tangent line. So that means The function values on the curve we can approximate using the tangent, okay, but only in the small neighborhood of where the tangent is drawn, okay, and we call it linearization, okay. So mathematically, if a function is differentiable at x is equal to a, okay, then the approximating function, okay, L of x is equal to f of a plus f dash a into x minus a. So we know what is this, okay, the equation, or the equation of this line, tangent line at the point A, okay, is the linearization of function at x is equal to a, and the approximation that the function values can be approximated by the points or the values at the from the tangent line uh, of f by L is the standard linear approximation of f at a, okay. The point x is equal to a is the center of approximation, so that means the point where we draw the tangent, that point is uh, called the center of approximation, and we can only approximate the function by the tangent line only in the small neighborhood of uh, this point, okay. So if we move away from this point, then the function and the tangent line may not give a good approximation, okay. Say for example, find the linearization of function is root of 1 plus x at x is equal to 0, okay. So uh, at x is equal to 0, if you are given this curve and we want to find what is the linearization uh, at x0, means at x0 if we draw the tangent line, then what equation that tangent line have, in one sense we can see, okay. So since this function is given 1 root of 1 plus x, and so we can calculate derivative of this as half of 1 plus x power minus half, and then we can use the linearization equation and calculate L of x, okay. And L of x is f of a plus uh, the derivative times x minus a, okay. So we need f of a and the derivative value at a, and a is x is equal to 0 point, so a is 0, so we can calculate f0 from here and f dash 0 from here, okay. And then we can use this equation, substitute all the values, and we can find that the linearization is nothing but 1 plus x by 2, okay. So that means we can approximate the this function by this linear function, okay, uh, in the small neighborhood of origin, okay. So graphically this is the graph of a root of 1 plus x, and at origin if we draw a tangent, then the equation of this tangent will be this 1 plus x by 2, and we can approximate the function values on this for this root 1 plus x by this tangent line in this small neighborhood of origin, okay. Say one more example with the same function value, that find the linearization of function this 1 by root of 1 plus x at point x is equal to 3. So at x is equal to 3, if we draw the tangent, then what is the equation of tangent? So we should get this, okay. So already fx and f dash x we have calculated, so if we calculate f3 and f dash of 3, okay, so by putting x3 here and here, okay, and then we can use this linearization equation to write that lx is 5 by 4 plus x by 4, okay. So that means this is tangent equation, okay. So we can approximate function root by this straight line, okay. So if you have quite complicated functions, then we can approximate the values by using these straight lines, okay. But you have to be careful that because if we cannot approximate at far away points, okay. The second thing that we are going to define is differentials, okay. So in derivatives we used two types of notations. One is the prime notation and other is the operator notation where we said that the if y is equal to fx is a curve, then we can denote derivative by dy by dx. So now we are here the numerator dy and the denominator dx are called differentials. Okay, so let us define and see what exactly dy and dx mean. Okay, so let y is equal to fx be a differentiable function. The differential dx is the uh, independent variable, and the differential dy is given by this equation. Dy is f dash x times dx, and so dy is a dependent variable and it is always dependent on x and the dx. Okay, so the variable dx is independent, and the variable dy is always dependent, and it depends on both x variable and the dx variable. Okay, so right, so dy and dx, they are called differentials. Okay, and if you calculate the ratio of the dependent differential dy to the independent differential dx, that means dy by dx, then it will be f dash x, which is the derivative of a function. Okay, so for example, let us do one example to calculate the differential dy. Okay, and just for record that the variable dx is often chosen to be the delta x, that is the change in x. Okay, so say find dy if y is this function fx, which is x raised to power 5 plus 37x, and then find the value of the differential dy when x is equal to 1 and dx is equal to zero point 0.2. Okay, so as said that dx is chosen to be, say, the change in x. Okay, so dy by definition is f dash x dx, and this is our fx, so f dash x is 5x4 plus 37. Okay, so we can differentiate. So dy, the differential dy, can be calculated or written as 5x4 plus 37 times dx. Okay, so that's our first result. And if I calculate the value of dy when x is 1 and dx is 0.2, so I can substitute x1 and dx as 0.2 to calculate that dy will be 5 plus 37 into 0.2. Okay, so that's 42 into 0.2 or 8.4. Okay, so given the dx differential, we can calculate dy differential. Okay, so as said that dx is often chosen to be delta x, the change in x. So what is the meaning here when we say that dy is 8.4? Okay, what exactly we mean that dy is 8.4? Let us see what is the physical interpretation of this dy. Okay, so geometric meaning of differentials. Okay, so let y is equal to fx be a differentiable function, and let x is equal to a be a point, and let us set dx as delta x. Okay, so let x plus dx be the neighborhood point of point x is equal to a. Okay, so let you have a point x is equal to a, and you have a neighborhood point a plus dx. Okay, so we have set dx to be delta x. Okay, so you have a curve y is equal to fx, so at point a the corresponding point is afa, and at point a plus dx the corresponding point is this a plus dx comma f of a plus dx. Okay, so dx is change in x, which is delta x. Okay, and we know that this is the change in y, delta y, which is a function value here minus the function value here. So change in y is function value at a plus dx minus function value at a. Okay, so the corresponding change in y equal to fx is delta y, which is the corresponding change in function values. Okay, but this if dx is delta x, this doesn't mean that delta y is dy. Okay, so to know what is dy, let us draw a tangent here. Okay, at the point a. Okay, and then let us calculate the corresponding change in the slope of calculate the corresponding values of the tangent line as point A moves to a plus dx. Okay, so what is the change in the tangent line L, the change from point A to a plus dx? Okay, so what is the corresponding change here, this height? Okay, so the delta L is L of a plus dx, means the value of at the on the tangent line at the point a plus dx, which is here. Okay, and minus L of a means the value on the tangent line at a, which is here. Okay, so what is the difference is this point minus this point. Okay, and this is a tangent to the curve, so we can use the linearization, okay, to find the equation of this line. Okay, for a given fx curve, by linearization this tangent line is f of a plus f dash a into x minus a, and if a plus dx is the neighborhood point of this, okay, close to this, then uh, we can calculate the values, approximate these values. Okay, otherwise we can calculate the values on this line by using the point a plus dx, so when x is a and when x is a plus dx. Okay, so in this case the value of the line at point a plus dx and value at the line at point a. Okay, so when x is a, okay, when x is a, this difference is 0, so value is f of a. Okay, so on this line, red line, the at a the value is f of a, and when x is a plus dx, so when x is a plus dx, the corresponding value on the line which is here is f of a plus f dash a, and x is a plus dx, so this becomes dx. Okay, so we can substitute the values from this equation here. Okay, so the value on the line at a plus dx is this result, and minus the value at a is fa. Okay, so this quantity is dx and fa cancels out, so we can write that it is f dash a dx. Okay, and uh, so this is nothing but we said that it is dy. Okay, dy is f dash x dx. Okay, if calculated at a point a, okay, then it is f dash a dA. Okay, so this height basically is our dy. Okay, so dy represent the amount the tangent line rises or falls when x changes by an amount of delta x or dx. So when this changes, when there is a change of x by amount of dx, then how much change in the tangent line occurs. So this height is our dy, which is f dash a dx. Okay, okay, and so the meaning of differentials, I think it is clear here that dy uh, is this height. Okay, or it is the amount the tangent line rises or falls when x changes by an amount of dx. Okay, okay, so now how we can graph the derivative of function from the if you are given the graph of a function, then how can we can graph the corresponding derivative function. Okay, so for this, let you are given this graph with the blue curve, y is equal to fx. Okay, and from the differentials uh, we saw that if we use the linearization at each point, and then we can calculate the dy and dx. Say for example, at this point if I draw a tangent line, okay, and then I can calculate what is my dy and dx, and the ratio of these two will give me the slope or derivative dy by dx. Okay, so at you can pick some points from the graph, and at each point you can draw a tangent line, and then you can calculate the vertical distance and the horizontal distance, and then not just distance, but if this is x1 y1 and this is x2 y2. Then uh, base will be x2 minus x1 and the height will be y2 minus y1, and so their ratio will be give us the slope value. Okay, so we can calculate slope at different points of the curve. Okay, and then we can plot a uh, x-axis versus the f dash or y dash uh, with those slope values we can plot. Okay, so for like at point here the slope is 0, so correspondingly on the x-axis we will get a point. Okay, and with a roughly we can join those points with a smooth curve to find the derivative curve. Okay, so for this curve, if we take the see that at the point A and at the point D the slopes are exactly 0, so the point corresponding point A dash is on the x-axis and the corresponding point D dash is on the x-axis. uh, at the point T we see that the uh, dy by dx is 2 units, so slope here or derivative is 2. So corresponding E dash we plotted here point as 2, okay, height. And similarly we calculate slope at some intermediate points like B and C and know the slopes by calculating the vertical and horizontal ratio. Then correspondingly we can plot B and C points, and then we can roughly with a smooth curve we can join these points to roughly sketch the derivative function. Okay, so from this graph we can see few things that where the rate of change of function is positive, negative or 0. Okay, so where the change is positive, where it is negative, and where the change is exactly 0, the rough size of the growth rate at any point x and its relation to the size of the function. Okay, so we can see where the growth rate is high and the corresponding what happening to function there, and the where the growth rate is negative and what happening to the corresponding function there. Okay, and also the where the rate of change itself is increasing or decreasing, so we can also see where this is decreasing and where it is increasing. Okay, so we can if we graph the derivative function from the graph of function, then you can utilize this method. Okay, now I leave this topic with one question which you can try to attempt, that to use the following information to graph the function f over the closed interval -2 to 5. Okay, the graph of f is made on closed line segments joined end to end. The graph starts at the point -2 3, and the derivative of function is the step function given in this figure here. Okay, so there is a derivative of the function is given here, and we have to draw a corresponding function, the original function whose derivative is this. Okay, and uh, so it is given that the domain is from -2 to 5, so derivatives are also given from there to there, and we have to uh, uh, draw f such that they are line segments joined end to end. So you can see that for example here from 0 to 1 the derivative is 0, means slope is 0. Okay, so we know when slope of the function will be 0. Okay, and there will be a horizontal function line. Okay, so corresponding to this there will be a horizontal line. Here the slope is 1 from 1 to 3 x values. When x varies from 1 to 3, the corresponding slope value is fixed constant number which is 1. So what should be the corresponding function value? Okay, okay, so if you note, just for example, if I write y is equal to 2 times x is a straight line. Okay, then we know the slope is 2 fixed for all x. Okay, so if the slope is fixed 1 for x varying from 1 to 3, so what should be the corresponding function here. Okay, similarly the slope is fixed and constant, and here also from 3 to 5 the slope is -1. So what should be the corresponding function curve. Okay, and so you can on the xy plane you can take start with this point -2 3. So at -2 3 is your point. Then with slope -2 draw the line, and we have to join each line end to end. So wherever that line end, from there you draw this line with slope 0 to 1, 0 slope. Then with next endpoint you draw a line with slope 1, and so on. Okay, so see what graph is generated. Okay, and then repeat the above process with the starting position -2 0 instead of -2 3. Okay, so instead of this -2 3 position, instead of starting from somewhere here, start from -2 0. Okay, and use this same uh, slopes. Okay, so corresponding graph what happens. Okay, and then compare these two graphs. Okay, so what do you see? Let me know through the comments what exactly you find when you draw the graph using the starting position this, and using the starting position this. Okay, and each time graph has to be joined end to end for these slopes. Okay. Okay, so I close this topic here. In the next lecture, we'll learn about some applications of derivatives, and to start with, we'll learn about extreme values, finding maximas and minimas, and we'll talk about the mean value theorem also. Okay, so till then, have a very good time.